Alright, Algebra 1 kids, this is Mr. Kim. Again, this is the lesson that you weren't here for. Or you were here during fourth period and you just need another, quick, actually this is not going to be quick because I'm going to go through a lot of material, but another, once over with the material we did. This is the line of best fit lesson. A lot of this is old, meaning the line of best fit, this concept of line of best fit, you already did extensively in Math 8 last year. But we are going to add an algebra twist to it, and then we're going to take it up not just one notch, but about 2-3 notches. What this unit is really about is this thing called regression, which means finding the line of best fit, or the curve of best fit, or the exponential function of best fit, or the quadratic function of best fit, using the data, and not just doing it with an eyeball technique, which means just kind of using a ruler and trying to figure out, okay, this looks about right. But this unit is going to be focused on finding the absolute line of best fit, so the best line of fit, and then using that to make predictions and gather data, or predict more data, understand how strong the data is, why is the data strong or weak, is there anything in between that makes it stronger or weaker. So basically it's a big statistics unit, and that's why we're taking our time with this, but this is the introduction. So again, today though is the ground level work. So we do need to make sure you get this, so please pay attention. I'm going to read for us, and let's get this started. The championship is on the line between Tinker Toy Tech and City College. Robbie plans to attend TTT next fall and desperately wants to see the game, which has been sold out for weeks. Surveying the exterior of the stadium so he can't get in, Robbie discovered a small drainage pipe that has a direct view of the field. The stadium is being prepared for the big game, and a maintenance van is currently blocking the view from the pipe, but the van will be removed prior to the game. So look, if you look down, here's the situation. Here's the game. Okay, it kind of gives some units here. We'll go over that in a second. Robbie's going to stand right here, and he's going to look through this wall, this pipe, this drainage pipe, and through the pipe he's going to be able to see the field. Problem is, if you kind of use your hands to make a tube or a makeshift tube in front of you and look through one eye, the closer you are to something, the less you can see, but the further you are, you can see a little bit more. So what I recommend doing is just taking, a paper towel tube and just testing it real quick. And, everything in front of you that's within maybe 1, 2, 3 feet, you're only going to be able to see pretty much whatever the tube diameter is. But then if you step back far enough and something's 100 feet away, you can actually see most of what's in front of your view because the objects are so far away. So if you understand what I'm saying, hopefully it's clicking. If this concept of what I'm explaining to you is not making sense, you want to actually grab, a paper towel or toilet paper roll, just the actual roll part, and just put your eye in it and kind of walk forward and walk backward against the wall to see what I'm talking about. So the south end of the field is 50 yards from the end of the pipe, so that would be his point of view, right? So he's here, but he starts seeing from here, okay, the field, and that's 50 yards. And the total length of the playing field, including the end zones, is 120 yards. So if you don't know anything about football, this end zone is one team's touchdown, and that's 10 yards wide. Then you have 100 yards of playing field, and then you have another 10 yards for an end zone. So altogether from end to end, that's 120 yards total. Again, the playing area is only 100 yards long. The width of the field is 53.3 yards. And the pipe will be at the center of the south end. The width of the field is 53.3 yards, or 160 feet. Investigate how much of the field Robbie will be able to see when he looks through the pipe at game time. To assist Robbie with this problem, we need to create a model to collect data. Your teacher will provide you with a view tube that has the same dimensions as the pipe through which Robbie will be looking. Record the length and diameter of your team's view tube. And then gather 8 sets of data points by measuring 2 distances. Your distance to the wall in inches and the width of the and the width of the field of view in inches. So everything we're doing that we're modeling means just like a scale model, we're testing it. It represents what's happening in real life, but it's only a model, so it's only it represents the real thing, but it's not the real thing. That's what a model really is. So we're doing it in inches, but realize up at the top we started talking about yards because this is a football field. So please understand that we're going to have to convert some units here. Not right now, but later. Okay? So let's continue to move on here. Now, obviously, you're not going to actually do this at home. I'm not going to make you. But if we were to do it in class, you would look through a tube and someone would back away from the whiteboard, and every time they backed away, we would see that they would be able to see more of the whiteboard. So the amount of view they could see from side to side would increase as they backed away from the whiteboard until they hit the back of the room. So what we're going to do is model that. So copy down this table, okay, and we're going to fill in this table. I'm going to give you values to fill in, okay. Distance from wall in inches. So this is someone backing away from a wall, and the width of field of view. This is not the field like football field. This is how much you can see, okay. So I'm going to give you some data because I simulated it myself, and I want you to copy this down. All right, so here we go. So pause the video if you need to write down the table, and then unpause when you're done writing the table down, and then you can write down the values. So if someone is 144 inches away from the wall, all right, so in other words, imagine my classroom, imagine the whiteboard where I stand, and imagine someone who's 144 inches away, right? So that's a pretty far amount of distance. If they're 144 inches away and they're looking through something like a hollowed out paper towel tube, right, the brown cardboard tube, they can probably see about 20.7 inches of my whiteboard, okay, and we're talking diameter, right, we're talking the width of a tube. If they are getting closer and they're about 132 inches away from my wall, they can see about 19.6 inches of my whiteboard. And then as they get closer, 120 inches, this number is going to obviously decrease. Now they can only see about 17.3 inches of my whiteboard. And as they again move closer, 108 inches, that's about 9 feet, and 108 inches, no, that's not 9 feet, never mind. Wait, no, that is 9 feet. And then when they're 9 feet away, they can see about 16.2 inches of my whiteboard. And we're going to keep going. 96 inches, see 14.8. 84 inches, see 13.1. 72 inches, that's 6 feet away from my wall, or my board, and that's going to be 11.4 inches. This is all in inches, okay, don't forget. And 60 will be 9.3. So 5 feet away from the wall, or 5 feet away from an object using the tube, they can see about 9.3 inches of viewing width, right? If that makes sense. So they're getting closer to the wall. As they get closer, the amount of the wall they can see is actually less and less and less. So this is scatter plot data. So if you look at the directions, the length of tube, I'm not going to write that down yet. We're going to figure that out using... yeah, it doesn't matter. Length of tube doesn't really matter. All right, make a scatter plot of your data. Describe the association between the field of view and distance from the wall. If you need a reminder about how to describe associations, see the math notes box in lesson 4.2.1. So the data is going to go away, and I'm going to scroll down to the math notes box. Okay, so data is going to disappear. So pause the video if you need to copy this down. Here we go, 3, 2, 1. All right, scrolling down. Actually, I can't scroll here. Let me. There is no math notes. Never mind. Wait, let me check. Okay, there's no math notes box. Oh, lesson 4.2.1. Okay, never mind. I didn't even see which lesson we were on. Okay, if you need to describe association, let's just review association real quick. Let me put the data back up. Oh, too bad. Too late. Association, you're going to talk about form. So form is going to be, is it going to be linear, nonlinear? Then you've got direction, so positive, negative. Then you've got strength, strong, weak, moderate. And then you've got outliers. So after you graph all the data that I had here previously, you're going to describe the form, the direction, the strength, the outlier. For example, you can say this is a positive linear strong association, or positive linear weak association, or positive nonlinear strong association with 2 outliers or with no outliers, something like that. And then part C says draw a line of best fit that models your data and will allow you to make predictions. Remember last year you guys made a line of best fit, you calculated the slope, you calculated the y-intercept, and then you used it to predict future values. What is the equation? That means you need to write down your equation. Now, everyone's is going to be a little bit different. I will eventually give you the equation that I want you to use for the sake of the rest of the classwork, but for now, figure out your own slope, your own y-intercept, which means you're going to look for lattice points after you graph. All right? And then you guys are going to answer, what do the slope and y-intercept represent in context of the problem? Think back to last year. You know, we would interpret the slope. For every 1 inch increase in yada, 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 the height increases by this many, or something like that. And then the y-intercept is when x is 0, x depends on whatever, let's say x is shoe size. When a person has no shoe size, their expected height was about 2 inches, something like that. So that's what interpreting the slope and y-intercept is. And again, I'll help you with that. So what I'm going to do now is, real quick, you guys pause. You guys make your scatter plot, describe the association, draw your line of best fit. Now, what I'm going to do is fast forward, so to speak, and I'm going to show you what the data should look like. Okay? So here we go, 3, 2, 1. So here's what the data should look like. Again, here's the data table with all the information. I'm using Desmos here just because I want to present it, right? Obviously, it'd be harder to record what I'm doing if I had like a camera. So don't use Desmos yet. We will use Desmos like crazy this unit, but not yet. Okay, not yet and not now. So I don't want you to use Desmos because you still need to know how to draw your own line of best fit. Okay, so there's the data. If you made your data well, oh, I forgot to tell you, you shouldn't have done one of these. This will be bad if you do. Let me erase that. If you did one of those truncated graphs, right? That's not good. What it does essentially is it shortens your y-intercept sometimes, or doesn't make it accurate, especially if you do it on the x-axis. Some of you might have done this, right? And you'll start here with, let's say, I don't know, 50, right? What that does is when you draw your line of best fit, you're missing out on 50 pieces of data, 50 units here, technically, so that's not really your y-intercept. So that's a bad y-intercept. So if that's what you did, I'm sorry. Don't erase your data, just erase. Like, watch what I do. Just erase this portion, right? And then make it longer. And you might run out of room. Just add another sheet of paper, tape it. You know, do whatever, right? Like you're at home. You can figure it out. It's not hard to do. You just added more work for yourself. In any case, what you should end up with is something like what I've shown you. Okay, so let me get rid of that. Right, so that's the scatter plot. You can tell the form should be strong. I'm sorry, the form is linear, definitely. Strength is strong because they're pretty tightly knit together. You can kind of see the line. And it's going to be positive as far as direction goes. And there are no outliers. Okay. Now, all of a sudden, there's going to be a line of best fit that appears because with the magic of what I can do, I can make that happen. So just watch. In 3, 2, 1. Bam. There's the line of best fit. Now, it's a little thick because I'm in projector mode, so I'm going to unprojector mode this just to help you guys see what it really looks like. So that's what the line of best fit would look like if I didn't have such a thick line. Now, some of you might be saying, Mr. Kim, that's not actually the real line of best fit. Yeah, that's fine, but that's okay. Now, I gave away my secret, so I'm just going to get rid of that. Anyway, if you caught that, great. If you didn't, just keep wondering what just happened. In any case, that's the line of best fit. So I'm going to go back to projector mode. I'm going to tell you what the equation is. Now, if you got your own line of best fit, hopefully it's something close to this. The line of best fit should be about y equals 0.13x, so you might want to change your fraction into a decimal, plus about 1.6. If you look at this y-intercept here, right, if you look at that y-intercept here, it's in between 1 and 2. It's a little bit above 1.5, so it's 1.6. And I'm increasing 0.13 units every time I move up 1. Now, obviously, my intervals are not 20, or it's not 1. These are 5, 10, 15, 20, 25, 30, 35, 40, right? So the slope is representing that, but if I actually count intervals, it's not good because my y's and my x's are not the same intervals. So again, this is what I've calculated. So from now on, I want you to use this as your slope and y-intercept. So keep your own equation, but for the rest of the classwork, let's use this equation. Okay? So go ahead and keep that. Okay, so that's the line of best fit. Not really going to talk much about it because we already discussed a lot of the content. So let's go back and answer the question now of the classwork. What do the slope and the y-intercept represent in context of the problem? So let me make some room here. Well, remember, our equation was y equals 0.13x plus 1.6. So let's interpret the slope. Okay, if you remember the graph, I'm going to draw a quick graph here. This was the distance from wall. And this was the width, like the width of view, or view width. So x represents how far you are from the wall, and y represents how much of the wall you can see as a result of how far you are. So that's the dependent, that's the independent. So what we're going to do is we're going to interpret the slope. When we interpret the slope, what we need to do is just put a 1 underneath it, and let's use the units to help us understand what we're talking about. So if you remember, slope is delta y over delta x, which means this is an x-coordinate. So my x-coordinates were distance from wall. These were in inches. So I'm just going to abbreviate my words, distance in inches from wall. Delta y was, or the y-axis was the field width of view, so how much of the wall I could see. So I'm going to say view here, and that was also in inches. So what we're going to do is we're going to interpret this using the numbers we have. Remember, I said I want you to use my equation, right? So you have your own equation. Hopefully it's close, but we're going to use mine. And we're going to interpret the slope. So the slope is this. And you're going to have to probably pause and rewind because I'm not going to write this. The slope is that. Sorry, something paused. So I don't know where I left off. So I'm just going to assume that, yeah. Well, anyway, there was some amount of time where I was talking and my iPad froze. So this might seem weird, but just roll with it. So let's interpret the slope one more time. So that means for every 1 inch distance away from the wall, right, or as the distance from the wall increases by 1 inch, right, the field of view, or the amount of wall you can see, or I can see, increases by 0.13. Why is it increased? Because both of these are positive. So if one of these was negative, then eventually we would say decrease for one of these. So as you increase the distance away from the wall by 1 inch, the amount of wall you can see, or the view width, increases by 0.13. That's how you interpret your slope. Interpreting the y-intercept, that's this guy. Remember, that's 0, 1.6. 0, 1.6. Remember, x is the distance from the wall. Y is the field width of view, or how much of the wall you can see. If I am 0 distances or inches away from the wall, right? That's wall. That means I can see 1.6. Or view. Let me erase C and put view. That means I can view 1.6 inches. How is that possible? Well, remember, I told you we're looking through a tube to mimic what, I forgot what his name is, Bobby? Let's just call him Bobby. I forgot. So Bobby is looking through a tube, and what we did was mimic that by imagining that we're looking at a tube at a wall in my classroom. So if I'm 0 inches away from the wall, I'm literally standing on the wall. But remember, I'm looking at a tube, so I can see 1.6 inches of the wall. And that's possible because a circle has a diameter. So that 1.6 is the diameter. 1.6 is the diameter. So interpreting the y-intercept just means, hey, I'm 0 inches away from the wall, or if I'm not standing away from the wall at all, we can see, or I can see, or you can see 1.6 inches of the wall. Does that make sense in this context? That absolutely makes sense. Because if I'm standing not away from the wall at all, so standing at the wall, because I'm looking through a tube, I'm looking through the diameter, and the diameter is 1.6 inches wide. Okay? So that's what that means. Anyway, this is going to go away in 3, 2, 1. Pause if you need. Rewind. Right? Here we go. 3, 2, 1. All right. Moving along. Predict how wide in yards, and there we go, Robbie's field of view will be at the south end of the field. How wide will it be at the north end in yards? So let me just kind of guide you. I'm not going to do it for you. Just remember, your equation is 1.13x plus 1.6. These are all in inches. So what you need to do is convert, right, what we have in terms of the picture into inches. So right now, if we predict how wide in yards Robbie's field of view will be at the south end of the field, remember, I'm going to draw the quick picture here. Here's the tube. South end of the field is here. That's the south end. And that's 50 yards away. Okay? So we have to convert 50 yards into inches because this problem is in inches. Find how many inches when we predict, and then crank it back out into yards. So I will demonstrate this with one problem. So how many inches are in a yard? Well, 36 inches makes 1 yard. So if I have 50 yards, that means I have a ton of inches. So you're going to multiply 50 times 36. Okay? 50 times 36 inches is going to be a certain number. I'm going to make you figure that out. I'm not going to figure that out for you. Then what you need to understand is, what did I just get? Did I get an x value or a y value? Well, remember, x is how far you are from the wall. Y is how much you can see. So predict how wide Robbie can see. Oh, his name wasn't Bobby, it was Robbie. Predict how much Robbie can see. So we're predicting a y value since we know an x value. So this is an x value, whatever that is. Plug it in, crank it out, and once you get that answer, please change it back into yards, which means instead of times 36, you're going to divide by 36 to find out how many yards you have. And then you're going to do the same thing for the north end. Remember, the north end is the furthest away, right? So remember, there's 50 yards here, there's 10 yards at the end zone, there's a 100-yard playing field, and another 10. So north end would be the furthest end. Pause the video. I'm going to make you do that on your own. Here we go. 3, 2, 1. Moving on. All right. So on paper it says sketch the football field including the end zones and label the dimensions using a different color. Shade the part of the field that Robbie can see. In other words, you're going to have a trapezoid, right? Because if you kind of understand how to view something, he's going to be able to see, right? If this is a bad drawing, but if the tube is here, he's going to be able to see like a certain amount. This is not accurate by any means, but this is how much he can see, right? So how much can he see? Well, he's going to be able to see a certain amount. Maybe he's going to see this much. I don't know. Maybe he's only going to be able to see this much. I don't know. I don't know. Maybe he's only going to be able to see this much. I don't know. That's what you have to figure out. Okay? So we want you to find the area of the field of view. All right? In other words, how much of the field can he see? So if you get a trapezoid, please remember the area of a trapezoid. Okay, area of a trapezoid is 1/2 base 1 plus base 2 times height. So in other words, you're going to add your bases times by height, take half. What percent of the field would Robbie be able to see? You're going to find the percent. You're going to divide, obviously. And then part C gets you down to another question where you have to estimate probability, which goes back to last year. Again, I'm not going to do that for you. Okay, moving on. 3, 2, 1. And then that's it. All right. So then you start your homework. So I did most of the work for you. I did a lot of explaining. The rest is up to you, calculations. We will go over the classwork, not on Monday because I'm not going to be here, but on Tuesday. Actually, I can't go over the classwork on Tuesday. We can go over the classwork on Wednesday, but don't worry too much. Okay. The most important part of this lesson is being able to find the line of best fit yourself, right? Your own, not using any tools besides your eye and a ruler, and then being able to understand, do I have an X and a Y? And I know it got complicated because we started changing units from inches to yards, but that's just the Algebra 1 spin. What you need to focus on is being able to understand, do I have an X, do I have a Y, can I calculate? All right? And that's it for today. Hopefully that made sense. Good luck. And if you have questions, please email me. Have a good day.